Freezing is a common way to keep food fresh for a longer time. When lower the temperature of a food item below freezing, it slows down the chemical reactions and the growth of microbes and enzymes that can spoil the food. Frozen food stored at temperatures below freezing, typically around -18 Celsius, can last much longer, ranging from a few months to a year. The freezing point is when the first ice crystal forms, indicating a balance between liquid and solid. For pure water, this happens at 0 Celsius, which is 273 Kelvin. However, freezing food is more complicated because of free and bound water. Bound water doesn't freeze easily, and soluble solids in unfreezable water bring the freezing point below 0 Celsius. As freezing occurs, soluble particles increase, charging the freezing temperature. The initial freezing temperature is where the first ice crystal appears. The freezing rate is the ratio of the temperature difference from the product start to end temperatures to the freezing time. Indirect contact freezing systems involve the use of an intermediary medium to extract heat from the food product. Facilitating its freezing, plate freezers employ flat, refrigerated surface to sandwich and freeze the product. Air blast freezers circulate chilled air around the product, effectively drawing out heat and inducing freezing. Specialized freezers designed for liquid foods utilize indirect contact methods to ensure uniform and efficient freezing of liquid-based products. On the other hand, direct contact freezing system involve the food product coming into direct contact with the freezing medium. In air blast freezers, cold air direct contact with the freezing product to induce freezing, while immersion freezers immerse the product in a refrigerated liquid such as brine or cold water to achieve rapid and precise freezing, particularly useful for individually quick frozen, which is IQF items. The choice between this system depends on factors such as the type of food being processed and the desired characteristics of the end product.
The virtual experiment is started by inserting the data of the potato diameter, which is 5 mm, and the length 10 mm, and then change the final center temperature to -18 Celsius and the air temperature to -40 Celsius. Then the air velocity is also changed to 1 meter per second. After that, click the start experiment to obtain the data. Then the product is changed to water with the same variable with the same step. Then click the export data to convert the graph to Excel. After that, the exported data for temperature is renamed with temperature potato and temperature water. The time and temperature potato is selected to make a graph by clicking the insert interface, and scattered graph was chosen to make for this graph. Then the temperature water was clicked to add temperature data into the graph. After that, the graph was added with data label and also trade line. Lastly, the graph is beautified by adding the temperature versus time chart titles and also axis title. The other 5 virtual experiment is continued with the change of the variables, which is sample diameter, sample length, and air velocity.
From the graph, we can see that the freezing temperature of potatoes and water decreased when time increased at 1 meter per second, 5 meter per second, and 10 meter per second. This is because the temperature of water and potatoes decreased during the pre-cooling period as sensible heat were removed. The temperature of the water decreased to 0 degrees Celsius and remained until all the latent heat of fusion was removed from the water to convert it into ice, which means phase change occurred. The temperature of water decreased rapidly when all liquid water has changed into solid ice, as sensible heat was removed during the post-freezing period. The graphs for the potatoes were similar to the water, but with a little difference. The temperature of potatoes at which initial nucleation occurred and ice crystals began to form was lower than that of water due to the presence of solids in the potatoes. This deviation in temperature profile from that of pure water was due to the concentration effect during the freezing of potatoes. The remaining water became more concentrated with solute when more and more water was converted into ice. This caused the freezing point to further decrease, and this gradual change in temperature with additional removal of latent heat continued until potatoes consist largely of ice and solid food components, where -18 degrees Celsius were reached. The freezing temperature of the potato and water with the dimension of 10 mm times 20 mm also undergoes similar condition as that of 5 mm times 10 mm. This table shows the time required by a cylindrical potato with dimensions of 5 mm times 10 mm and 10 mm times 20 mm to reach -18 degrees Celsius with the air velocity of 1 meter per second, 5 meter per second, and 10 meter per second. This table shows the time required by the water in water cup with dimensions of 5 mm times 10 mm and 10 mm times 20 mm to reach negative 18 degrees Celsius with the air velocity of 1 meter per second, 5 meter per second, and 10 meter per second. This table shows the effect of air velocity on the freezing time of the cylindrical potato and water with the dimension of 5 mm times 10 mm to reach negative 18 degrees Celsius. Well, for this table, it shows the effect of air velocity on the freezing time of the cylindrical potato and water with the dimension of 10 mm times 20 mm to reach negative 18 degrees Celsius.
So for the question 1, discuss how the center temperature changes with time for samples of water and potato. Comment on the shape of the plot. So for the answer, the temperature change over time for water typically follows a linear trend, heating or cooling steadily. In contrast, the temperature change for a potato may exhibit a more complex plot due to the factors like moisture content and varying thermal conductivity in different regions of the potato water. Undergoes a line temperature decrease from 20 degrees Celsius to 0 degrees Celsius as sensible heat is removed during freezing. In the constant phase, the temperature remains at the freezing point until the latent heat of diffusion turns liquid water into the solid ice, this causing a rapid temperature drop. So for the potato, the freezing time is shorter due to the initial nucleation and ice crystal formation. Latent heat removal occurs faster than in water. The decreasing temperature continues until potatoes mix with solid components, removing sensible heat until the endpoint temperature is reached. The temperature plot for water is linear, while potatoes exhibit a more intricate pattern influenced by the factor like moisture and thermal conductivity. Initial absorption leads to a steep rise, followed by a gradual increase as the interior set heats up, with size and initial temperature affecting the overall shape. So for the question 2, discuss the effect of the air velocity on the freezing time. So it will elevated air velocity generally leads to a reduction in freezing time. The increased airflow enhances heat transfer between the food samples and the surrounding air, resulting in a higher heat exchange rate. This in return speeds up the removal of both sensible and latent heat, facilitating a quicker freezing process. However, maintaining a balance is crucial as excessively high air velocities may cause uneven freezing or surface drying, impacting the overall frozen product quality. So as air increases, the free time decreases due to enhanced heat transfer efficiency from the food sample. So the difference prompts water transfer between the product and its environment, leading to a concentration gradient within the product. Consequently, water moves from the interior to the exterior, followed by surface evaporation as the surface cools. So for the question C, on the water part, we got all the information here: density, latent heat, freezing temperature, freezing air temperature, thermal conductivity, and also heat transfer coefficient. So we will use the formula TF that given here. And for the diameter 5 mm, we will got the TF 6.51 mean after we substitute in the formula given. And next is air velocity 5 ms minus 1. So we will got also 6.51 mean. And for the air velocity 10 ms minus 1, we got the same answer, which is 6.51 mean. And for the diameter 10 mm, we will got the 13.37 mean. And next, for the air velocity 5 ms minus 1, we will got 13.37 m mean. And for the air velocity 10 ms minus 1, we will got 13.37 mean. Next, moving forward for the question potato. For the diameter 5 mm, we will got the answer 6.51 mean after we substitute in the formula given. Next, we will got for the air velocity 10 ms minus 1, we will got 6.07 mean in the after we substitute TF. And next, air velocity 10 ms minus 1, we will got 12.59 mean. And air velocity 5 ms minus 1 for the TS, after we substitute, we will got 12.59 mean. And lastly, air velocity 10 ms minus 1, we will got 12.59 mean.
In conclusion, freezing serves as a crucial preservation method for maintaining the quality of food products. The experiment focused on determining the freezing point of both solid and liquid foods, emphasizing the significance of freezing time. During the freezing process, energy is extracted, causing the substance to drop below its freezing point, leading to the transformation of water into ice and a change in the physical state of the substance. Subsequently, the temperature is further reduced, often reaching storage levels such as negative 18 Celsius. Utilizing freezing curve and phase diagram prove effective in illustrating the freezing process. Terms like pre-cooling, supercooling, freezing, ice nucleation, and glass transition are employed to describe various aspects of this process.